Today I want to present to you the demonstrating of BrainScale's 2 interchip pulse communication using the XTOL network, and briefly summarizing the BrainScale's architecture. So we are emulating biological neuron dynamics in analog electronic circuits, and spike events are digitized from these analog circuits and communicated between neuron circuits. Our chips and systems feature an accelerated model dynamics compared to biology. This means that, for example, in the BrainScale's 1 system, we have a speed up factor of 10 to the 5, and in BrainScale's 2, we have an acceleration of 10 to the 4 compared to biological time scales. In addition, BrainScale's 2 has 2 embedded SIMD processors on the chip. So up to now, these systems can only execute single chip experiments for BrainScale's 2, or experiments spanning a wafer module for BrainScale's 1. And we want to extend this to make it possible for these systems to work together and emulate larger neural networks. Therefore, we have to communicate neural events over packet-based network, and the requirements for this network are, due to speed up, quite high. So we need low latencies, as biomilliseconds translate to hardware microseconds, and bio spike rates in orders of hertz translate to hardware spike rates in orders of kilohertz. We also want to have the possibility of small packets, because the single event is only 4 bytes in size, and yeah, we don't want to waste much transmission data on header and protocol. Also, we need a high bandwidth, as we connect our chips to FPGAs for readout and communication with a link of 8 gigabits per second. An Ethernet network is not so good suited for this, because it has rather high protocol overhead. So for 8 bytes payload, we need at least 64 bytes transferred data per packet. Of course, these packets can be much larger, and then it becomes better, but yes. Then an alternative would be InfiniBand, but this is proprietary hardware and IP with limited access for us. So we found a viable alternative with the XTOL network, which was developed at the University of Heidelberg and is now a spin-off company. It was developed at the Computer Architecture Group at the Institute for Computer Architecture, and it offers bandwidths of up to 100 gigabits per second. With our FPGAs, we currently use 60 gigabits per link. The latency can go down to 70 nanoseconds per hop. So 1 hop is 1 traversal of a network card. With our FPGAs, we have had to reduce the clock frequency, so we have 150 nanoseconds per hop. The smallest packet possible in an XTOL network has an overall size of 40 bytes and also transports 8 bytes of payload, so it's better than Ethernet. And yeah, it offers, so 1 network card offers 7 links here. These are the plugs, and here's the 7th link, and thereby we can propose the 3D torus with concentrator nodes for the network topology in the full network, which is planned. So for the goal now is to communicate pulse events over the network and interconnect the emulated networks on several chips. Therefore, we want to overcome the header overhead, which is imposed by every packet-based network, and limit the message rate which is used on the network. So we accumulate events destined to the same destination FPGA in so-called bucket buffers. And yeah, then on the destination, we can receive spikes, event streams from different source FPGAs, which have to be merged for the target chip to be able to handle them. So then we have a first experiment set up here in the lab, which connects one source chip to one target chip. And yeah, therefore we have only one source. We don't need the merging yet. With this setup, we measured neuron to neuron latencies across the network from chip to chip of in between 1.6 and 2.3 microseconds, which is of course quite large compared to the 150 nanoseconds, but you have to take into account that there is 2 chip links and FPGA implementations in between. So it's quite understandable that this is more. So, and the latency range here is due to the interleaving of event traffic with host traffic at the network interface. Yeah. So now I hope I can do a live demonstration. Therefore, I have to change my screen share. Can you see the scope?
Yes.
Very good. So then I take my console on the screen and I can start an experiment. And you see the signal has changed on the scope. Here we can then measure the latency between the chip, the first source chip in yellow. So we have a neuron on the source chip, which is stimulated by regular spikes from a stimulus neuron, which is which is actually external input. So we have here at the first cursor a spike on the source neuron, and then the target neuron reacts at this point, and we have here a measured latency of 1.94 microseconds in between. So then we can play around with the source neuron and, for example, increase the interspike interval of the stimulus population, and then it looks a bit more untidy here. We see we have clearly less spikes at the destination, but the latency, of course, stays in the same range. We have again 1.9 microseconds here. We can play around a bit more and decrease the weight of the stimulus population, which then even more decreases the spike rate of the source neuron, and also because the weight of the destination neuron on the second chip here is also decreased, we see that the membrane needs quite more time to elicit a spike on the second chip. But again, the latency between the first spike on the source chip and the first reaction on the destination chip is quite similar. Okay. So yeah, that was my live presentation. I will just switch again the screen share to my last slide. So we are now able to basically support multi-chip experiments on Brainscales 2. And first experiments yield latencies of in between 1.6 and 2.3 microseconds from neuron to neuron on 2 chips. And the network size is horizontally scalable, so we can scale this up to more neurons and chips easily. The next steps will be synchronization of experiment execution across the FPGAs so that we can compare the readout data, especially spike trains and voltage traces. And we will fully support multi-chip experiments in higher software layers of our BrainScale 2 software stack. And of course, we will scale up these experiments for more than 2 chips soon. So thanks for your attention, and I'm glad to answer any questions.